Good morning. Hopefully you had a nice day yesterday. Maybe a day off, maybe day to catch up. If you're anything like me, you didn't get nearly as much done as you thought you would. That's okay. Happens every time. All right, so let's just do a quick recap of last day. So we started talking about exponential functions. So we'll just kind of highlight some of those things. And oh, I wanted to show you, I'm playing fast and loose with my iPad here, switching screens. Last day, it just kept, after our class, the class after yours, it just kept kicking out my screen share. So hopefully that doesn't happen again today. I rebooted everything. Hopefully we're okay. So what I did was I posted a couple of assignments, just quick little assignments, or I think they're very small, from section 4 or chapter 4, which is exponential and logarithmic functions. I also made a quick note. There are some compounding questions. So we talked about some compound interest problems last day, and I said I don't really expect you to know that semi-annually means compounded 2 times per year. So I just gave you the outline there, just for reference. Okay, so let's see here. Let's get back into it. And so let's do review. We talked about exponential functions. Exponential functions look like f of x is a to the power of x, where a is the base. Okay, that's important, especially for later today. And then what makes it an exponential function is that x is the variable, and the variable is up in the exponent, right? And so that's what makes it an exponential function. The variable is in the exponent, which makes it an exponential function. Oops. Okay. So whatever you have in here, that's your variable. And then if it's up here in the exponent, then you have an exponential function. And we said, okay, well, there are 2 general shapes to this thing, right? If you've got your y-axis and your x-axis here, then you can have exponential growth. In fact, I'll use a different color here. Exponential growth is where the base is larger than 1, is if a is greater than 1, okay? Of course, referring to a as the base here. And then we can have decay. What's interesting is they all pass through 0, 1, but we'll get to that later. Or actually, let's put it on here, 0, 1. And running out of colors here. I used that already. Here, let's put this 0, 1. I'll use dark green for the decay. So the decay comes down through 0, 1 and goes like this. So this would be exponential decay. Is if a is between 0 and 1, right? So we already established earlier or last day that, okay, we're not going to let this base be less than 0. It just complicates things. And so we're not going to let the base be less than 0. And if it's between 0 and 1, so up until 1, right? So some sort of fraction, then you've got this decay going on, whereas if it's greater than 1, then you've got this growth. Okay, so then we also talked about compound interest, right? So compound interest, only because I put some of these questions on your assignment. They're kind of the most typical easy exponential function problems. And they're good to know. So I know this isn't a business math course, but I mean, there's no harm in knowing how money works. So A of t, and I'll talk about what each of these are, is P times 1 plus r over n to the power of n times t. So first thing I want you to notice is that, well, the variable here is t, which is time. And t is in the exponent, so you have an exponential function. Okay? So A of t is the amount, after t years. Okay, this is also called the future value. So sometimes it's called the future value. P is the principal, so the initial investment. So we call it the principal or the present value, if you want to have that link between a future value and a present value, right? So the principal amount is the present value, or the initial investment / initial investment. Okay. Your R is the rate as a decimal. Okay, so 3% you have to convert to 0.03. Rate as a decimal. Oh, I'll add the annual rate. It's called the nominal rate, but the annual rate as a decimal. Okay. N is here and here, right? So N, let's put it over here, N is the number of compoundings per year. Number of compoundings per year. And oh boy, really running out of colors here. Let's do purple. T is time in years. So there are times where you have to do some conversions. So if I say, okay, you invest this $100 for 16 months, then you'd have to divide that by 12, right? 12 months in a year. So the time in years, T is the variable. And it is, oh, someone has their mic on. Are you hearing some feedback? Looks like everyone has their mic off. We have company, so there's some chitter chatter. They're being quiet, but maybe that's, yeah, that's it. Hey, they can hear you guys. So T is the variable. And since it is in the exponent, this is an exponential function. Okay. All right. So For these first problems, we don't quite know how to solve for things in the exponent yet. We will later today, so that's exciting. I'm never going to get you to solve for n. It's a little bit tricky with two of them here, so but I will get you to solve for t, and that's what we're building up towards today. But if you are given some future value, right, some final amount, then you can solve for p, right? I'll always give you the rate. I don't really see a point in solving for the rate, but you can rearrange things as long as you have n and t, so that you can take the n times tth root to undo it. So that's kind of the end of our review here. Well, let's see, what else did we do? Oh, yeah, right. We talked about the natural exponential function, which is kind of our go-to exponential function. So the natural exponential function is e to the power of x, okay? And e is just a constant, where e is roughly, so just like pi, we don't have, we'll never be able to know the full number. And if you continue, if you take calculus, and I think there is a kind of a group of you that tends to take some calculus, so then you'll see kind of more about the number e. But for our purposes, we're just doing 2.71828. Right, but use the E button on your calculator. Okay. One thing to keep in mind, if you're asked to give exact answers, the exact answer has to have the E still in it, right? As soon as you convert it to a decimal here, it's not an exact answer anymore, right? So that's just something to keep in mind if you're asked to give exact answers. Okie dokie, artichoke. Oh, I remember what I did here. Last day in our notes, what I did was I took a screenshot of the end of that logistic problem here. Okay, so, and good thing too, because it kept shutting everything down as soon as I went into Desmos. So hopefully that doesn't happen again. But one thing you have to notice is that when you're graphing in Desmos and you need E, so the problem we were working on was this one, right? And so we were given D, we were given K, and we were given C, and then T, of course, is our variable, which we can replace with X if we want to graph it. And so what we have, right, is we need E in the denominator, but you have to use EXP if you're graphing in Desmos. And like I said, that's pretty common that we just use EXP and then in brackets, whatever the power is. So, and then I just plotted points. So I let X be 20 and I drew a line and I found the intersection. I let X be 30 and I drew a line and I found the intersection. And that gives me the population at each of those time points. But then as time goes on, it looks like the population size plateaus at 1200. So now that's the end of our review here. Okay. Let's talk about continuously compounded interest. Continuously compounded interest is a little bit special. It's a special case of compound interest. And again, it's just a way for us to incorporate problems that use e to the x. And so n here is the number of compoundings per year. So for example, if you're doing 4%, so if your rate is 4% semi-annually, then at 2 time points in the year, so halfway through the year, you get 2%, and then at the end of the year, you get another 2% for a total of 4%. So whatever the rate is divided into the number of compoundings. At each compounding, what happens is the interest that you've earned gets tacked on to the principal amount. And then for the rest of that compounding period, for the next compounding period, you're earning interest on not just your principal, but the interest that you've earned previously. So, so the number of compoundings per year, right, determines how often you're compounding your monies. And so kind of a fun idea is to have continuously compounded interest. And so you invest your $100 and then continuously interest is being added onto it. What's weird about it is it doesn't change that much how much you end up with in the end for the same amount of time. So continuously compounded interest, let me go steal that little blurb here. Hey. Okay. So continuously compounded interest, notice that we're still talking about A of t, which is the final amount or the future value. So here we can call this the future value. P is still the principal amount, so the initial investment. R is still the interest rate per year, but notice that it's quite a bit of a simpler equation than what we were dealing with earlier. So this only works for continuously compounded interest, right? And so you want to keep an eye out for, are you compounding continuously, or are you compounding quarterly or monthly or whatever? So R is the interest rate per year as a decimal. And of course, T is the number of years still. So what I want to do is I want to do a little comparison here between the two. So that's why we had to introduce the other equation earlier. So if 600 is invested at an interest rate of 2.5 per year, 2.5%, remember we have to convert it to a decimal per year, find the amount of the investment at the end of 10 years for the following compounding methods. So we're going to look at annually, semi-annually, and quarterly, and continuously. I think, just in the interest of time, let's just look at annually, right? So just once a year you're compounding versus continuously, and do a little comparison. So we'll just do A and D, and then I'll leave the B and C to the reader. That's you guys. That's what textbooks always say, right? We'll leave these as an exercise to the reader. So first off, right, I'll bring in my equation here, or maybe what we should do is we should outline all the information that we're given. P is 600, right? Because that's my initial investment, right? So 600 is my P. The interest rate is 2.5% per year. Okay, so that's annually. And so my R is 2.5 divided by 100, right? I need to convert it to a decimal. So it's going to be 0.025. Yeah. And I think, did these ones have that fancy percentage button? I think so. 2.5. Yeah, so if, I don't know why they put these buttons on calculators actually, but there is a little percentage button over the answer key. So if you go shift percentage, so if you put in 2.5 and then shift percentage, it'll give you 0.025, or you can just divide it by 100. But you want to make sure you have the right number of zeros, otherwise it could make a mess. So what else are we given here? So 2.5 per year, and then so find the amount of the investment at the end of 10 years. So T is going to be 10 years. T, remember, has to be in years, but because it's in years, we're good. And we want to find A of 10. Okay. So the first one, right, the first three actually use the same formula. It's just that our n is changing here. So n here is 1, n is 2, and n is 4. And that's why I put that list on your Moodle page, right, where in case you're not sure, quarterly especially, because sometimes they'll say every 3 months, right, which is 4 times per year. So that one's a little bit tricky, but just remember quarterly n is 4. Okay, so for A, we have P of T, oops, sorry, P of T, A of T. A of T, so I'm just gonna grab that formula that we introduced earlier today, saw earlier today. P times 1 plus R over N to the power of N T. Plugging in all our values here, A of 10 is what we want to find, right? And so we're going to let T be 10, and P is 600 times 1 plus 0.025 divvied up by N, which in this case is 1. That's the only thing that you're going to change as you go through. So if you do B and C, right, only N is going to change. Everything else is going to stay the same. So that's why we only need to do one of these. So 1, and then 1 times 10. So when we're doing these calculations, right, you want to be really careful that you start in the middle of these brackets and then you kind of bloom your way out. So 0.025 divided by 1, 0.025, plus 1. Then you have 1.025, which you're going to raise to the power of 10, and then you're going to multiply it by 600. So how I'm going to show that is at each step, I'm just going to simplify a little bit. If you wanted to, you know, kind of skip straight from here to 1.025 to the power of 10, that's totally fine. But I just want to show you all of the steps. Of course, here, since I'm dividing by 1, I can skip it. So 600 and 1.025 to the power of 10. 1.025 to the power of 10 is roughly 1.28008. So 600 times 1.2800844544, roughly. I always write out as many decimal places as I get on my calculator. It's kind of hard to stop. So I want you to keep all your decimal places, even if you don't write them all out, you have to keep all your decimal places in your calculator. Just because we're talking about money, so of course it's important, but presumably anything that you're talking about or measuring is going to be important. So then times 600 puts me at 768.0507265. Because it's money, right, I can round it to 2 decimal places and not feel bad, but I'm not going to round until the very end. So this is going to be $768.05. So here, since we are talking about money, we can round to 2 decimal places. We can round to 2 decimal places. But not until the very end. But not until the very end. Okay. So if we've got $600 and we're compounding annually at a rate of 2.5% per year for 10 years, where we would end up is $768.05. So that's compounding annually. So just compounding once per year, nothing crazy. Let's do a comparison of compounding continuously. So that's where all the interest is being tacked on just continuously. I can't even go that fast. I guess I can like this. Doesn't really help as a visual though. So D is compounding continuously. So we just had the formula here. I'll bring it in again. Oops. Lose my calculator in the paper shuffle here. A of t is p times e to the RT. So it's just a special case where we've got e instead of some sort of a base a, right? So e is our base, and this is how we calculate continuously compounding. So continuously compounding, we use this different formula. So again, we want to find a of 10, which is going to be 600 times e to the rate, which we decided was 0.025. Oops, 0.025 times 10. So again, just keeping in mind, okay, so we've got this 0.025 times 10 in the exponent, and so we need to simplify that before we can raise e to the power of it, and then multiply by 600. So just step by step here, I get 600 times e to the power of 0.025 times 10 is 0.25. Okay. And then e to the power of that, e to the power of 0.25 is roughly, so 600 times 1.284025417. And then times 600, 770.41525. And again, since we're talking about money, let's go 770.42. One rounds up because it's followed by 5. So the difference between these two, just able to squeeze it on the same page here, 768.05 versus 770.42. There is a difference, but it's up to you whether it matters or not, right? And so it just kind of depends on the scenario. Of course, if we're talking 600,000, then yeah, I care a little bit more, right? What if you get some sort of perk if you go compounding annually instead? I'd probably go for it, right? And so the difference the difference between compounding annually which was 768.05, just so I have it here, and compounding continuously, which was 770.42, is, oh, let's see here, 770.42 minus 768.05, a whopping $2.37. Awesome. Okay, so like I said, I know that this is not a business math course, but it is kind of one of the most accessible types of problems that we can have is dealing with money. So looking at this general exponential function, because t is in the exponent and we've got this general base of 1 plus r over n, and then the natural exponential function, which is e to the power of rt. So we've got this kind of dual situation of showing how to do things. Okay, so I haven't seen any questions, so let's start talking about logs. You've probably dealt with logs before, but I'm going to pretend that you haven't so that we start from the bottom. But just out of curiosity, have you guys dealt with logs in any of your other courses yet? No one knows. Maybe not yet. I know you do eventually, but maybe it's next term or something. Okay, so logarithmic functions are, we've barely mentioned it. Okay, so kind of it's been said, but not really done, sounds like. Cool. So logarithmic functions are the inverse of exponential functions. So that's going to be important to keep in mind. So logarithmic functions which we can just call logs. Logs are the inverse functions of exponential functions. Functions. So it looks a little bit strange, but I just want to highlight that, okay, if you have an exponential function, then you have this variable in the exponent, right? And so the inverse is what undoes whatever function it's the inverse of, right? So we talked about inverses. We can use the inverse cancellation properties. We can do a ton of things. But so knowing that it's the inverse of an exponential function tells us that it's how we undo exponential functions. So this tells us that we use logs to undo exponential functions. To solve for x in the exponent. So like I said earlier, right? We don't have a way quite yet to solve for t here, right? And we don't have a way to solve for t here either. So, but now that we're introducing logs, that's where we're going to be able to bring this t downstairs and be able to solve for it, right? So if you have something you need to solve for in the exponent, you need to use logs to undo them. Okay. So we use logs to undo exponential functions, which means to solve for x in the exponent. Okay. So this next blurb, though true, it can be a little bit confusing. So I'll just bring it in and we can talk about it. So the logarithmic function, if you let a be a positive number with a not equal to 1, okay, so we talk about a logarithmic function with base a, and so again, we've heard of that base a, right, in our exponential function. In fact, because they're the inverses of each other, they're very much related. So log base a is defined by log base a of x is equal to y is the same as saying that a to the power of y is equal to x. And I always have a hard time kind of linking these two. I find it very difficult. But if you read it as, and I also don't find this very helpful, but it is a crutch that I use a lot of the time. So if the log base a of x is the exponent, okay, so if y is equal to the log base a of x and a to the y, right, is equal to x, so log base a of x is the exponent to which the base a must be raised to give x. Now, if you just kind of bounce around here, and I'll draw it even bigger here, log base a of x equals y, right? If I just take a to the y equals x, right? So what this looks like is a to the y is equal to x. So sometimes we'll have things like the log of 10 or log base 10 of x equals 2. So if you're solving for x, then you have log base 10 of x equals 2. Well, 10 to the power of 2 equals x, so x must be 100, right? So for example, log base 10 of x equals 2 means that 10, right, so you take your base and make it the base of your exponent and then raise it to the y is equal to x. Means 10 to the power of 2 equals x, right? So x is 100. Okay. You read this as log base a of x. Okay, so here, log base a of x is read log base a of x. Okay. Just to clarify, I just went ahead and said it and used it, but it's important to say. Okay. We're going to have easier ways to solve for x, right? And even looking at things, how do we solve for y here? And so we're going to have easier ways to do this than to make this type of connection, right, that we just did here. But it's important to notice that they are linked. So they are the inverse of each other. And so that's going to be important. Okay. Let's see here. Before we go any further, I want you to use your calculator to evaluate some of these. Now, what's tricky, tricky and nice, I guess, is if you have a calculator like this, I think, or like this, right? So some sort of fancy scientific calculator, I think you had to buy one for the program. Often there is, so on mine, try to see if I can see here, there's a log and then an empty base and then an empty entry. And so if you have a button like that, then you're gravy, right? You don't have to figure out how to convert between the bases. It's done for you. But in Desmos, if you're using the Desmos calculator, dare I go there? It kept booting me out last day, so here we go. My Desmos calculator here. Okay, it's still with me. If I go to, let's see here, not ABC, the functions, notice that it only has a plain log and the ln, which we'll introduce in a little bit here. It's just the natural log. There's no log with an empty base. And so what that means is we have to know how to calculate bases. And we'll introduce that in a little bit. But for now, I'm just going to assume that you have a button. And then if you don't, just hang tight and we'll use the change of base formula in just a little bit. Okay. Use your calculator to find these. You should have, I'll put it on the next page. How about, you should have, I'll try to kind of copy it like it's shown on my calculator here. A log empty base, empty entry button. Okay. Which lets you put in any base and any entry. Okay. So if we do something like 27a, for example, log base 6 of 36, okay. If you use your calculator, you should get log base 6 of 36 is 2. If we think about it, 6 to the power of 2 is 36, right? And so, and that's the link that we established up here, right? 6, so the base to the power of the y is equal to x. Another way we could look at this is to say 6 to the power of what equals 36. 9 to the power of what equals 81. 7 to the power of what equals 7 to the power of 10? Well, 7 to the power of 10 equals 7 to the power of 10, right? So even though it looks bad, if we know this link between the base and the y is equal to x, right, then we can kind of see the connection here. So, or 6 to the power of 2, or yeah, I'll write it out in words. 6 to the power of 2, no, we didn't have the 2. That's why it was all in words. 6 to the power of what equals 36? Well, 6 to the power of 2 equals 36. So y equals 2. Let's do, that was A. Log base 9 of 81. Well, 9 to the power of what equals 81? I suspect it's 9 to the power of 2. Let's just confirm. Yep. So 9 to the power of what equals 81? Well, log base 9 of 81 must be equal to 2. We'll do this last one just so we kind of see the connection here. Log base 7 of 7 to the power of 10 equals 7 to the power of what equals 7 to the power of 10? Well, it's equal to 10. Confirm these using your calculator, right? Just like we did up here, we started with our calculator and then we said, oh, we can probably unravel this, right? And so what we have, right, is log base 9 of 81. Let's just try it. Log base 9 of 81, oops, try 80, is 2. Okay, good. How about log base 7 of 7 to the power of 10, making sure it's all inside the log brackets while I get 10, right? So it works out, of course, but it's just good to see those connections. Okay, so let's talk about properties of logs. So some properties of logs, eventually these will come just kind of second nature, but to get there, we have to, I don't like to make you memorize stuff, but until it is kind of second nature and you're comfortable working with logs, you will have to memorize these. Okay, so memorize these. Memorize these properties. Okay. Otherwise, we're going to have a really hard time working with logs, right? And so we have to memorize these properties until they're second nature. Until they are second nature. Okay. And they will be, and it won't take long. And a lot of these are just kind of pretty basic, right? And so if we have a look at the first one, for example, well, log base A, to get to 1, A to the power of what has to equal 1? Well, anything to the power of 0 is 1. So, okay, fine. So any log base anything of 1 is just going to be 0, right? So we can kind of reverse it and say, well, any log of 1 is going to be 0. Log base A of A is going to be 1 because A to the power of 1 equals A, right? So we've got that link, right? And most often, if I have, log base 7 of 7, I'm still going to try it on my calculator. So I don't really need to memorize this one because I will find that it's 1, but it's just good to have in the back of your mind. So now here, log base A of A to the x is x. Now, we already saw that, right? Log base 7 of 7 to the power of 10, well, that's got to be 10 because to get to 7 to the power of 10, I have to take 7 to the power of 10. I know. It sounds obvious, right? But I know when you're dealing with these things, they're not that obvious. And so, but this is a key concept, right? And so what we have is if we have A to the power of x, and I want to solve for x, okay, then you can just take the log of the same base and that'll drop down the x, right? Because what happens here is you have the log base a of a to the x is equal to x. So if you have a choice, then if you're trying to solve for x, then if you have 3 to the power of x, right, you can take log base 3 of 3 to the power of x, and that's going to give you x. Okay. Same thing here. If you've got an x inside the log, then log base a of x, then you take the base and raise it up. Okay. So we will specifically use, instead, I'll say we will use 3 and 4 extensively when solving for x. Right? Doesn't look like it, right? But each of them drops out an x. Okay, so scenario 1. Uses point number 3. Okay, is if you have something like 5 to the power of x equals 2. Okay, and you have to solve for x. What we can do, as long as we apply the same thing to both sides, we can go ahead and do it, right? It doesn't alter this equal sign, right? So what I'm going to do is to bring this x downstairs, or to solve for this x. Well, I've got 5 to the power of x. So what I can do is I can take the log base 5 of 5 to the x. So then on the left-hand side, it's going to drop to x. But on the right-hand side, I also have to take log base 5. Right? And so then use property 3, right? That log base a of a to the x equals x. So what you do is you have log base 5 of 5 to the x equals log base 5 of 2. Okay. What happens here, when you take log base 5 of 5 to the x, you use this property that the x drops out, right? So I just kind of imagine that if you're taking the log base 5 and then of a base 5, well, those are just going to cancel and the x drops out. All right, so then you get x is log base 5 of 2, which you can calculate on your calculator. Log base 5 of 2. So x is roughly 0.43067655581. Okay. This is the exact answer, log base 5 of 2, and this is your approximate answer. Okay. But that's how, so when you see x as the power, right, what you need to do is you need to kind of latch on to these properties and figure out how you're going to get that x outside. And so this is how we're going to bring it down. You look here and you see the base. Okay, I've got a base 5. So then I'm going to take log base 5 and drop it down. Okay. So we'll come back to this property, of course, because it's a big player. But scenario 2 is if you have something like, let's see here. Which uses the 4th point. Let's say you have log base 8 of x equals, I don't know, 10. Okay. So now what we're gonna do here is, okay, so I've got my x inside the log. So how am I gonna extract this, right? If I use the fourth point, which says, okay, if you need to get at an x, right, and you have log base a of x, then you can raise it to the power of a. Notice that it's kind of the opposite of what we just did, right? So a, take that base and put everything to the power, or in the power. So 4, use 4, which says that a to the log base a of x equals x. So what we're going to do is we're going to have 8 to the log base 8 of x. Oops, this was part of the original. Equals 8 to the power of 10, right? So what you do to one side, you have to do to the other side, right? But that's how we're going to get this x to drop out. So then from here, right, a to the log base a of x, 8 to the log base 8 of x is going to be just x. So x is 8 to the power of 10, which is going to be huge. X is 10737418824. Huge, huge. So that's how we're going to use these properties. So depending on if you've got an x in the power, right, then you need to take a log to bring it down. Or if you've got an x in the log, then you need to take the power to bring the x down or isolate the x. Okay, so let's talk about, all right, bring in the graph first so we can see it, see this thing. So if we have y equals a to the x, right, an exponential function, in this case we're talking exponential growth, then the log, so the logarithmic function, it's going to be a reflection about the origin, which is kind of confusing, I think, right? But what happens is, so for the logs, just like the exponential function has a range of from 0 to positive infinity, right? Now, remember the properties of the inverse says that, okay, well, the range becomes the domain and the domain becomes the range. And so what happens here is our domain is from 0 to infinity, not including 0, right? And then our range is all real numbers. So recall that for exponential functions, the domain is from negative infinity to infinity, right? You can plug in any value of x and you can get a number. The range is from 0 to infinity. Okay. Now, since the log is the inverse of this thing, the domain and the range, they flip. Okay. Since the log, or the logarithm, is the inverse of the exponential function, the domain and range switch. So for logs, the domain is 0 to infinity, and the range is from negative infinity to infinity, or all real numbers, right? So the range, it'll give me any value of y that I could possibly need. It's got this kind of curvature here, but what's important is that the domain, I cannot plug in a value of x that's less than 0, not even 0, right? And so this is going to be important. And I'll bring in, I've got it highlighted already. Okay. So we cannot take the log of 0 nor a negative number, right? And so that's going to be really important for checking our answers, right? So if you're solving for x inside a log, okay, so if you're solving for x inside a log, then you can get negative answers, but just remember that a negative answer doesn't work in the log, right? So there could be negative options, as we'll see, but you have to remember that, okay, x has to be positive, so it can't be 0, and it can't be negative. So it has to be just strictly positive. Therefore, an x inside a log base A, okay, just open for any base, must be strictly positive. I can't remember if I have. So on the next page, there are a couple of examples. We'll just do 1 or 2 here. Okay. So first things first, let's do 74. Okay. And so we've got f of x is the log base 5 of 8 minus 2x. And remember, so all these problems that are in the notes, I've posted the solutions already. So I encourage you to go through more of these on your own and just kind of make sure that you're on the right track. Okay, so if you've got log base 5 of 8 minus 2x, remember the base doesn't matter, the logs all behave the same. So what we're saying is that this has to be greater than 0. So the domain is that 8 minus 2x must be greater than 0. It can't even be equal to 0. We can't take the log of 0. In fact, you can try, I encourage you to try log base 10, it doesn't matter what the base is, of 0, and you should get some sort of math error. So you can try it, but it doesn't work. And so that's kind of a nice crutch too. So now if we want to solve for x, right, what I'm going to do is I'm going to, just because I don't like dealing with negatives, I'm going to add 2x to both sides. Adding 2x doesn't change the direction of the inequality, right? The inequality only switches direction if we multiply or divide by negative. Right here, I'm adding 2x, so I'm safe. So I get 8 must be greater than 2x. And so now I'm dividing by 2, positive 2, so it still doesn't change. So 8 divided by 2 is 4. X has to be less than 4. Just check with some numbers, right? 8 minus 2 times 4 is 0, so that's not allowed. So, okay, so x has to be less than 4. In fact, let's write it like this. X has to be less than 4. notice that the arrow just follows that x around, even when I switch it, right? X has to be less than 4. It's just easier to read it that way. So if we let x be 3, for example, that's less than 4. 8 minus 2 times 3, 8 minus 6, that's 2. That's allowed. Okay, so that's how I'm going to make sure that my inputs are actually in the domain. Okay. Kind of a trickier one is maybe this one, right? So let's do 78. We're going to find the domain of h of x, which is the root of x minus 2, minus the log base 5 of 10 minus x. Okay. Notice that there are restrictions. So from before, right, we've got restrictions on our square root. We can't take the square root of a negative number, but we can take the square root of 0. Whereas here, we can't take the log of a negative number and not even 0, right? So the overall domain of this thing is going to be where they overlap. Okay, so here, we're going to have, we can't take the square root of a negative, and over here, we can't take the log of 0 nor a negative. Okay. So as far as our domain kind of repertoire goes, it's always been, okay, we can't divide by 0. So anything that makes us divide by 0 has to get pulled out of the domain. We can't take the square root of a negative number, okay? We have to pull it out of the domain if that makes it happen. Now, our third thing that we're going to add on is that we can't take the log of a negative number or 0, right? And so we can only take the, it's easier to say we can only take the log of a positive number. So if we can't take the square root of a negative number, well, then I better make sure that x minus 2 is greater than or equal to 0, right? And so x minus 2, I'm going to add 2 to both sides, just keeping in mind if I multiply or divide by negative, I have to switch that inequality. And so x has to be greater than or equal to 2. Fine. How about over here? 10 minus x has to be greater than 0, so it cannot be equal to 0. 10 minus x has to be greater than 0. Notice that it's easier to write it out symbolically than it is in words, or at least I find it is, right? To kind of capture all the nuances here. 0 is not included, has to be greater than 0. So if I'm solving 10 minus x has to be greater than 0, I can add x to both sides, so I get 10 must be greater than x, and then I just kind of revolving door it because I like to have x on the left. X is less than 10. Okay. The overlap of these will be the overall domain. So the domain is the overlap of these two. Okay, because it has to satisfy x has to be less than 10, but it also has to satisfy x has to be greater than or equal to 2. I find it's easier to do a number line, right? And so I guess I'll put it on. I only need one more line, so I'm going to just bump this up one line. Because if I put x equals 2 on here, right, so here I'm at 2, and it's including 2, and x has to be greater than or equal to 2. And then if I put on 10 here somewhere, x can't be equal to 10, but it has to be less than 10. And so here I've got an open dot. So the overlap here is going to be including 2, so a square bracket at 2 up until 10, but not including 10. Is, oops, I said square bracket and then I did a round bracket. 2 to 10, not including 10. So that would be the domain of this whole thing. A little bit trickier, right? But all we're doing is we're adding another condition to the roster, right? If we're taking the log, it has to be of a positive number, if you want to think of it that way. Okay. So the special case, ln, you've probably seen it on your calculator, but that's the natural logarithm, and it's just the log base e. So just like we had the natural exponential function, now we have the natural logarithm. And we call them the natural exponential and natural logarithm just because they occur naturally in a lot of different phenomena. And so here we can bring in all these properties of the natural logarithm, but I want you to realize that they're the exact same properties that we just established. So these are not new properties. They're just a special case base e. So the logarithm with base e is called the natural logarithm, and we denote it by just ln. So the natural logarithm ln is log base e of x. And if you wanted to, you can write log base e of x, but often we get lazy and we just write ln. Same idea though, if ln is actually log base e of x, then we take the base to the power of y equals x, e to the power of y equals x. Same thing that we just established earlier. Same thing as before, right? Log base a of 1 is always 0 because a to the power of what equals 1? Well, a to the power of 0 is 1. And so log base e of 1 is still 0, and you can try it on your calculator, right? So these are all, these properties are the same as for log base a of x, but with the special case of base e, I'll say. So they're the exact same. You don't need to memorize these because they'll fall out of what you memorized earlier. So the natural log of e is 1, right? E to the power of what equals e? E to the power of 1 is e, right? Same thing here. Notice that this is how we're going to solve for x if we have e to the power of x, right? Then we take the natural log, and then it drops out and gives us the x. Same thing if you've got the natural log, then you raise it to the power of e to get at that x, right? So again, we use these properties to solve for x. Okay? But nothing happened here. We're just introducing this special case of ln and just showing that it behaves the exact same way. Let's see here. I wanted to do this one. The others are very similar. So a certain strain of bacteria divides every 3 hours. Okay? If a colony is started with 50 bacteria, then the time t in hours required for the colony to grow to n, capital N bacteria is given by, okay, so t is the time that it takes, is 3 times the log, and I guess I haven't introduced the common log. Where did I miss it? Okay, fine. Hold that thought. I skipped it on the other page here. The common log is log base 10. I should introduce it because when we write log with no base, it's implied that it's base 10. Okay. So log x is the common log, which is base 10. And I'll hang on to that one for just a little bit. ln of x is the natural log, base e. For a lot of calculators, these are the only 2 buttons that we have. Okay. On many calculators, these are the only buttons we have. Okay. I will show you how to get around that in just a little bit, but including Desmos, which is weird, right? They should be able to handle a special log base whatever button, but I think the developers are maybe being a little bit picky and saying, hey, they should just learn how to change the base. I suspect. Okay, so the reason that I kind of halted here was because, hey, there's just the log no base, right? And so that's when I remembered I hadn't introduced the common log yet. But so the time is how long it takes for this thing to grow to n bacteria. So 3 times the log base 10, right? Or just log of n, so that's the number of bacteria that we're at, divided by 50, probably the initial bacteria, presumably, divided by log 2. Okay? Find the time required for the colony to grow to 1,000,000 bacteria. So if we want 1,000,000 bacteria, you know what? I'm going to put it on the same page here. So we have t is 3 times the log, and I'll make a note here, base 10, of course, of n over 50 divided by log 2, or the log base 10 of 2. Log 2 is just a number, right? And once we plug in n here, it's also going to be just a number, right? And so we get 3 times the log. Usually I end up going cursive on this thing. Just kind of feels easier. 1,000,000, so 1, 0, 0, 0, 1, 0, 0. Okay, divided by 50, all divided by the log base 10 of 2. First thing we're going to do is we're going to simplify this 1,000,000 divided by 50, right? Because that's what I'm taking the log of. So here we go. Make sure you get all your zeros. 1, 2, 3, 1, 2, 3, divided by 50. I get 20,000. 3 times the log of 20,000 divided by the log of 2. So if we take the log base 10 of 20,000, 1, 2, 3, okay. I get 3 times roughly 4.3010299996 divided by the log of 2, log base 10 of 2, 0.3010299957. So now, because I want to have all my numbers in my calculator, I'm going to redo log base 10 of 20,000 and then multiply it by 3 and then divide by this. So 1, 2, 1, 2, 3 times 3. So I get 12.903089999 divided by roughly 0.3010299957. So divided by log base 10 of 2 to get the closest to the exact value that I can. Of course, because I'm working in decimals, it's approximate, but I get 42.86313714. Okay, so what does that tell us? The time in hours, right, is T. So for 50 bacteria to grow to 1 million bacteria, it's going to take 42.86 hours, right? Careful with minutes, because 0.86 minutes is not 86 minutes or seconds or whatever. 0.86 you have to multiply by 60. Anyways, I'm not going to make you do that, but just be careful if it ever comes up. So roughly 42.86 hours. Okay. So good, good, good. I want to, oh, decision time, huh? Do I keep going into the log laws? Remember, what we cover by the end of today is going to be on your test on Tuesday, but I also want to talk a little bit about the test and see if you guys have any questions. So maybe what I'll do, I was hoping we'd get through 4.4, but that's all right. Let's leave it for now. Sound good? So, the test, I'm committing. The test on Tuesday will cover up to here. Okay. So for the test, right, you're gonna do, well, let's go all the way back here. We started in functions, right? And so we talked about functions, we talked about the domain of functions, which we came back to today. We talked about some common graphs. What else did we talk about? Lots of things, maximums, minimums, increasing, decreasing functions, average rates of change. Just flipping through our notes here. Linear functions, right? So straight lines, and then we got into transforming functions. So going from a core function and kind of manipulating it until we've transformed a function. Then we got into combining functions, inverses of functions, compositions of functions. Then we talked about quadratics, right? graphing quadratics, putting quadratics into standard form, finding the vertex, and finding a lot of the information, the x-intercept, the y-intercept. And then we talked about polynomials and their graphs, polynomial long division. Oh man, we did a lot. And then graphing rational functions. So just as a recap here, chapter 2 was on functions. And of course you have the notes. Yeah, so all of 2, 3, and then 4, and then we didn't actually do 4.4, we'll stop at 4.3. But chapter 2, chapter 3, which I can't remember what it was called, polynomials, probably. And then 4.1 to 4.3, which is exponents and logs. So now that I know where we're cutting this thing, I'll put up a practice test, okay? But for the actual test, what we're gonna do is the same thing as last time. So I'll put up a PDF at the beginning of class on Tuesday, and then you'll have, you know, the class time to work on it, and then I'll give you a bit of a buffer to submit it on Gradescope, and that's where you're going to submit all your work. So I will post the PDF of the test at the beginning of class. I guess it'll be available then. I'll post it before. At the beginning of class on Tuesday. So I'll post the PDF of the test at the beginning of class on Tuesday. You have all class to work on it. Class to work on it. And then when you're finished, scan your work. And upload to Gradescope. And I'll give you, when does this class, so we go 8 till 9:50, how about till 10:15? 10:15, or I'll do it like this. So that should give you lots of time to, and of course, who am I to judge if you kind of use that time to upload, but that's your deadline for uploading. Anything after that will be late and penalized. So that gives you, what, 25 minutes to scan and organize and upload your work. I do expect it to be nice and organized, and you've assigned all your questions, right? This is our second time doing it, and I know you're using Gradescope already, so you're probably pretty good at it by now. It's not bad. So that's 25 minutes to upload your work. It should be plenty. Okay, any questions? So now I guess I'm cutting it short. Okay. I'll stop the recording, but if you have any questions, then let me know.